Welcome, this is a very quick video talking about Gauss's law for a point charge. So first let's draw up our charge. We're going to have charge Q here, and of course the first thing we're going to do is to draw out some field lines. So those are going to come out radially from the center. And so if we wanted to know what the electric field was at a point r, a distance r away from that charge Q, then this is the equation you would of course write down. It's just the charge Q divided by 4 pi epsilon naught, that's just a constant, times r squared on the bottom. So that's this 1 over r squared term, which we know about. And then at the end we of course have a vector symbol, little r hat, which tells us the direction of that electric field. And the direction, to be clear, is always going to be along these field lines. So it's going to point radially away from the charge. Okay, so the next thing we want to do is we want to draw a surface around this charge. And so here I'm going to be thinking about drawing a circle around the charge. And then I'm going to try and work out the flux through that closed surface. So of course I say circle, I mean really it's a sphere in 3D, but we can simplify things by just thinking about the 2 dimensions of the board here. So okay, so what have I got? Well, this is of course the equation you want to use to calculate the flux. It is the integral over the closed surface, so that's indicated by the little circle around the integral sign, of E dot dA. So E here is of course the electric field, it's a vector, you can see it up at the top, and dA, this is the surface elements of those surface. So we take the whole surface, the sphere, and we chunk it up into tiny little small elements, which we call dA, and dA is a vector which points, not tangentially, orthogonal to the surface. So it points directly out of the surface. Okay, so now you can see the reason why I chose a sphere. The symmetries of this problem, of this electric field, mean that the electric field is always spherically symmetric. What that means is that the dAs for a sphere are always going to be parallel to the E's, the electric field. What that means is that I can take the magnitude of the electric field out of this integral, and I can write it like this. It's the magnitude of the electric field, and then I just need to perform the integral over all of those little remaining surface elements, the dAs. What is that integral? Well, it's the integral over the surface, over the whole surface of all the little dAs, so of course it's just the area of the sphere itself. I write that as a sphere here. Okay, let's pop that equation up over here. So this is what the flux through that closed surface, that closed sphere is. It's just the magnitude of the electric field times the area. Well, of course, we know how to calculate a few of these things. First off, the area of the sphere is just 4 pi times r squared, so we can plug that in. And secondly, the magnitude of the electric field, as we said before, is just Q divided by 4 pi epsilon naught r squared. And so we now have the r squared on the bottom and also a 4 pi on the bottom, which is going to cancel with the 4 pi r squared coming from the area of the sphere. So now we see that if we simplify this a little bit, the flux through that sphere is just given by Q, which is the charge of the point particle at the center, divided by epsilon naught. And this is precisely what Gauss's law tells us. If we take a closed surface around a collection of charges, then the flux through that surface is going to be the enclosed charge, in this case Q, divided by epsilon naught. Notice 2 things here. Firstly, although we used a particular surface, a particular sphere with a particular radius r, that r ended up cancelling. So if instead I used a sphere which had radius 2r, then it would also cancel in exactly the same way. I.e., this result is independent of the radius of the sphere that I choose. In fact, better than that, it's in fact independent of what kind of surface I choose. So I could instead choose a box or any other sort of shape, and I will get the same answer. The difference being that it's slightly harder to calculate these things because we're not using the symmetries of the problem to make our life simple. Thank you very much.